There is one thing that we have left out of our combined gas law, because we've talked about how, pressure can change a gas. We talked about how volume can change a gas. We talked about how temperature can change a gas. But there's one other way we can change a gas that that we haven't talked about. Because let's say we've got a tire. If you want to increase the pressure in the tire, there are a couple ways you could do it. You could increase the temperature. All right. If you increase temperature, the molecules go faster. They strike the walls of the tire at a higher speed, and so they put more force, and so you increase the pressure. You could decrease the volume. If you decrease the volume of the tire, then basically you are packing more molecules into a tighter space, and so more molecules will hit each surface area of the tire there. But you don't use either one of those whenever you need to basically increase the pressure in your tires in your car. You don't say, "Oh, my tire pressure is a little low. I'm going to go and drive to Mexico so I can have a higher temperature." Or you don't say, "Oh, I'll just squeeze my tires in tighter so then I have a higher temperature." Common sense thing here is what you do. You add air to your tires. All the cases we've done before have assumed that basically that the number of molecules or number of moles of gas that are in the container stays the same. But we can't always assume that. And so the combined gas law can be modified to include the number of moles of gas. And because what we know is this, is if we increase the number of moles of gas, then we're also going to increase the pressure. That means they're going to be directly proportional. And so the proper place to put this is we're going to put our number of moles of gas on the bottom. So it's this is sort of a modified combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. And so this is sort of our modified version. We won't really see this one very often, but you need to know it's out there. And this one lets us take account the number of moles. Now, with pressure, volume, number of moles, and temperature, these are the only four things which affect the behavior of an ideal gas. Nothing else does. If I want to change the pressure of an ideal gas, I can only change the volume and the number of moles of the gas and the temperature, and that's it. Nothing else makes a difference. If that's true, then if I have any set of pressure, volume, number of moles, temperature, that's going to equal that. So that's the before, right? So we've got our I've got sort of our before for this, and we've got our after for this. Now, what if we change it to another after? Well, we're going to get some other after, call it after 2, and then we could get some other after, call it after 3. It's always going to equal the same thing. All these things are equal. The before, the original before, and the after 1, and the after 2, and the after 3, they're always equal to some number. And so if they're always equal to some number, then that means we can say that for any possible set of conditions of pressure, volume, number of moles, and temperature, doesn't matter what they are, they're always equal to some number, which is going to be basically a constant. And so this constant here is going to be sort of what we're going to talk about here. So the two sides are equal for all possible factors, then both sides are going to equal constant. We're going to call this constant R. And so we could sort of rewrite this a little bit as P1V1 over N1T1 equals P2V2 over N2T2 is equal to this constant R. This constant R is called the gas constant. And so we'll see a little bit of this in a second. Sometimes it's also called the ideal gas constant. But this is our gas constant right here. And this is true for all gases, for all pressures, all volumes, all temperatures, that this P1V1 over N1T1 equals P2V2 over N2T2, or P a trillion V a trillion over N a trillion T a trillion is equal to R. This one number right here. So let's take a look at what we would do with that and how that becomes useful. If for any value of P, V, N, and T, it's equal to the ideal gas constant, it's equal to this gas constant, we really don't need to worry about our numbers. Why not just say the pressure, the volume, the number of moles, the temperature? Get rid of our subscripts and just say, let's assume the gas isn't changing. Let's just assume we have a gas that has a certain pressure, a certain volume, a certain number of moles, and a certain temperature. If you do that, we can sort of rewrite this as being just PV over NT is equal to R. Now, we don't like having this division sign in the middle, so let's just go and take our NT and move it up to the top. And we do that, we end up with an equation that looks like this. PV equals nRT. This is the ideal gas law. Because this is true only for ideal gases, which we said most gases we run into act a lot like this. And so PV equals nRT. This is our second of our major gas laws. So we have the combined gas law that basically puts together Boyle's and Charles and Gay-Lussac's law all together. And now we have our ideal gas law that takes care of gases that basically aren't changing. Combined gas law deals with gases that change. We start with one gas, we change it to a gas that has different conditions. The ideal gas law lets us figure out that if we just know the pressure and volume and number of moles of a gas, we can find the temperature. No problem right there. Now, talk a little about R right here. So we said R is a constant, but we haven't said what it is. R is a gas constant. It's basically equal to 62.36 torr times liters divided by Kelvin moles. Okay? So R can be different for different units. And so if we were doing this in kilopascals rather than torr, then we would have a different value of R. If we were using, instead of liters, milliliters, we'd have a different value of R. But for the purposes of this class, we're going to go ahead and we're going to use 62.36. But because we're using 62.36 for R, that means that when we do this, our equation here, our ideal gas law here, the pressure is going to have to be in torr. It means the volume is going to have to be in liters. Number of moles as well, obviously just in moles, no problem there. The temperature, as before, has to be in Kelvin. And so basically what we've got here is, unlike the combined gas law, where you can use any unit of volume you want to, or any unit of pressure you want to, as long as it's the same on both sides, the ideal gas law requires that you use a certain set of units. And in this case, the certain set is torr and liters and Kelvin and moles. And so pressure has to be in torr, volume has to be in liters, temperature has to be in Kelvin, and moles obviously has to be in moles if you're going to use 62.36, which we will for this class. So let's try a little bit example-wise on this. So 0.076 moles of methane gas are collected at 35 degrees Celsius and 814 millimeters of mercury. So the question is, what is the volume of this gas? So to do this is that we say this gas is basically not changing from one thing to another. Since it's not changing, we're going to use the ideal gas law. And so PV equals nRT. And so do we know the original pressure of this gas? It says it's at 814 millimeters of mercury. Now, what we know is the pressure has to be in torr. So in this case, we're going to have to convert from millimeters of mercury to torr. Fortunately, that's easy because 1 millimeter of mercury is equal to 1 torr. So this is just going to be 814 torr. Got lucky on that one. Times the volume. Do we know the volume? It says, well, what is the volume? So we don't know that. So that's just V. Equals N. N is the number of moles. And it says here our number of moles is 0.76. Our unit is moles, as we said here. Times R. And so let's look and see what is R. R, the gas constant, is 62.36. And so then for R, we'll put 62.36. And then lastly, times the temperature. The temperature has to be in Kelvin. We're told it's 35 degrees Celsius. And so then you'll basically go ahead and do it the same way we did before, is we want to convert this to Celsius. So we say 35 plus 273.15. And so we get 308.15. And so 308.15 Kelvin is our unit here. And so at this point, we've got everything. Just want to solve for V. So let's divide both sides by what's on the left here, 814, so that we get our volume by itself. And so we would say then multiply it out. So 0.76 times 62.36 times 308.15, then divided by the pressure, 814. And so when we do this, we get a volume of 17.9414. The unit here, we said, is going to have to be in liters. So we know it's liters right here. Significant figure-wise, taking a look at that, what we see is that we have 814, 3 significant figures. We have 0.762. 62.36 is basically is a conversion factor. It's a constant. And we said for the purpose of this class, anytime we're given a conversion factor or a constant, it's going to be considered to have infinite significant figures. And 308.15 is going to be, since we start off with 35 degrees C, it's around to the ones place. It's going to be around the ones place here, so we'll have 3 significant figures, 1, 2, 3, like that. And so our final answer is going to have 2 significant figures. So our final volume here is simply going to be 18 liters. And so that is how you use the ideal gas law. So let's try out another one. Let's see another example and see how that works. So, in this example, we're told 15 grams of oxygen gas are generated by the decomposition of potassium chlorate. The gas is measured to occupy 1.2 liters at standard pressure. And the question is, what is the temperature of the gas? So in this case, the gas is not changing. So as a result, we're going to use our good old friend, the ideal gas law. And so to use the ideal gas law here, we'd say PV equals nRT, same as it has before. Do we know the original pressure? Well, let's see. It says 15 grams of oxygen gas are generated by the decomposition. The gas is measured to occupy 1.2 liters. That's standard pressure. Standard pressure here is, we'll have to find it the proper units. In this case, the units we need to use are torr, millimeters of mercury. And in torr, standard pressure is 760 millimeters of mercury, or 760 torr. And so times the volume. Do we know the volume of the gas? It says it occupies 1.2 liters. Okay, and it is in liters, so that's the right unit here. Equals N, the number of moles. Do we know how much oxygen gas we have? It says 15 grams of oxygen gas. So we don't have the number of moles, we do have the grams. But we can find moles from grams, so we're going to set up our table here. So we say 15 grams of oxygen gas, that's O2. And we want to get rid of grams of oxygen gas, and we want to go to moles of oxygen gas. And so in this case, how do we find the number of moles? Look at the periodic table. Oxygen is 16, there are 2 of them, so it makes 32 grams in 1 mole. And so in this case, you go ahead and we want to multiply across the top. So 15 times 1 divided by the bottom, 32. And so in doing this, we get a final answer of 0.46875 moles of O2. And so that's the number we're going to use for the number of moles here. So 0.46875. Note we don't round yet because we're not done with the problem. Times our ideal gas constant here. And so the gas constant, because of the fact that we're using torr and liters and all that, same one we always use in this class, 62.36. And so for R, you put in 62.36. And then lastly, times the temperature, which is what we don't know. And so that's what we're solving for. Similar to before, to solve for the temperature here, we're just going to have to divide by the 2 guys that are next to the temperature. So divide by 0.46875 and divide by 62.36. And we're going to say the same thing over here because I don't feel like writing it again. And so it cancels on this side, and we should be just left with the temperature. So we'd say 760 torr times 1.2 liters divided by our 2 guys that are going to be on bottom, which is 0.46875. And then 62.36, and we do that, I get a temperature of 31.19. And so we get an awfully cold temperature here. And so, because this has to be in Kelvin. And so 31.19 Kelvin. Significant figure-wise is, let's take a look at what we were given here. We had 760 torr, but it says standard, this is standard pressure. And so this is exact, so that has infinite significant figures. 1.2 liters has 2 significant figures. The number of moles here was based on our 15 here. Now, since that's spelled out, it means it's also going to be infinite. If it was just 5 grams, it would have 2 significant figures for this, so we just use 0.46 like those two. And 62.36 is also infinite. We've only got one thing that's going to determine this. That's going to be our number of liters, which has 2. So our temperature is going to have 2 significant figures, so our final temperature is 31K. And so we have an awfully cold gas of oxygen here. And so that's our final answer. That's how you, once again, use the ideal gas law. So let's take a look at one last thing. Our one last note is this. How do you know which one to use, whether it's combined gas law or ideal gas law? Whenever you have a case where the gas is changing, where the pressure started off as one thing and now it's something different, the volume started off as one thing and now it's something different, you're going to use the combined gas law. So anytime the gas changes pressure, volume, or temperature, or some combination of those, you're going to use the combined gas law. You'll use the ideal gas law when either the gas is not changing, that is, it just tells you here's the temperature, here's the volume, here's the pressure, or something, or some combination of those, or you only know the pressure, volume, temperature, or number of moles for a gas at one particular time. And so you could have a case where basically you said you have a gas that starts off at 100 kPa and is compressed until it has a volume of 5 liters and it's at 200 kPa and so on and so forth like that, where you're given a lot of information about one state but not enough information about the other state, then you'd still use the ideal gas law. So as a general rule, combined gas law for cases where the gas is changing, ideal gas law for cases where the gas is not changing. And so those are basically ideas on how you're going to know which gas law to use. But these are our two main gas laws we have here. So combined gas law, to some extent, goes beyond Boyle's and Charles's and Gay-Lussac's law because it sort of combines them all into one thing. And the ideal gas law lets us figure out what a gas is doing even when it's not changing.